Well, hello. Welcome to the session on astrobiology and the future of life, evidence, analogy, and prediction. I'm very excited with the group of people that we have to talk. Because of the number of people, we have very strict timelines, so I'm going to give everyone 10 minutes. If there is a chance for a question at the end of a talk, we'll go ahead and have that question, but 10 minutes per talk, and then we'll have an open discussion at the end. So I hope you'll think a little bit about this question of the future and how we think about it well. Let's go ahead and turn things over to Catherine Denning.
Hi there. Can you hear me and see my screen?
We can.
Good. That's good news. Okay. All right. Thank you. So I'm setting my timer for the fabled 10 minutes and off we go. So as you can see, that is my talk title. As an anthropologist, I am probably expected to use pictures of people, but I could not shake the desire to use trees, partly playing with the idea of what the tree of life really looks like. But they're all metaphorically meaningful trees, not just pretty inspirational ones. If you want to know more about what they kind of stand in for, just ask me. So yeah, my contention is that some anthropological lessons learned the hard way might aid astrobiological thinking. When Lucas and I first talked about this session, I just thought it was such a fantastic idea. That question of what constitutes good research on the future of life. And I'm really looking forward to hearing other people's wisdom on this. So I am, very grateful to Lucas for, whoops, I don't want to annotate my slide, for suggesting that we do this. And also congratulations to Lucas on his recent tenure as the Bloomberg Chair at the Library of Congress. Yay. And thanks to Frank and the organizing committees for all that they've done. I particularly appreciate being able to participate in this as a hybrid session. I'm really grateful for that. So here's just the overview of what I'm going to try and cover. First, I'm just going to recap extremely briefly some key points from Lucas regarding persistent ascent narratives, which are a really good jumping off point for us. I'll say a little bit about my approach to this topic. I've worked on various parts of this quite a bit. There isn't a lot of time here, which forces me to be very blunt and distilled. But obviously, I've got a lot of stuff on my ResearchGate and academia.edu if you might be interested in reading some of my extended papers on this. I'll give you some brief observations about what anthropologists and archaeologists have learned the hard way that might be worth knowing about ditching unilineal narratives, remembering agency, unpacking the unified we, considering your sources, being careful about collapse and contact in particular, rethinking human-animal and human-technology relationships, and also actually being in the present. Just a note as well that, there's no tidy conclusion to this one, but I do have a question about our future-y habits and obsessions. I also just want to plug a session tomorrow, which includes philosophers, social scientists, and a futurist. So you might want to come out for that. Right, so it is a real pity that Luke couldn't deliver his talk in this session, but I do hope that you caught it yesterday or that you can watch the recording. There's a couple of key points from it that I would like to highlight as we begin. I hope that Lucas himself can circle back to these in the panel discussion at the end. So yeah, there's where you go to see the recording. From his full abstract here, so he talked about the traditional ascent narratives, which described a journey in spiritual as well as physical space. You remember the nested spheres, kind of medieval notion of the cosmos. And then how the Copernican revolution decoupled spiritual and physical elevation. But he points out that ascent narratives remained. They remained popular as biological theories of progressive evolution from lower to higher life forms. Of course, Darwin's theory of evolution disproved those theories, and Lucas notes that sociologists observed concrete harm through theories of more and less advanced individuals and societies. And I'll have a little more to say about that later. But despite this, Lucas points out, many scientists continue to promote ascent narratives that predict normative social development through science, radio astronomy, and rocketry, all up to interstellar colonization. And he points out that such linear narratives are inconsistent with modern evolutionary theory and should be replaced by narratives of diversification and local adaptation, to which I say, Amen. I certainly think Lewis is right. And in his extended argument, he's got the evolutionary biology theory, a theology, and history. I'm just going to try and weigh in just a smidgen from the social science angle as we consider how to think about the future of life. So my contribution here, can't see who's in the room. I know some of you, but probably not all of you. Anyway, I'm an anthropologist and an archaeologist with a background in archaeological theory, or what we think we know about the archaeological past and how we think we know it. So these epistemic questions, which are really important when you're dealing with, tough data sets and partial recovery and all the things that archaeology is deliciously plagued with. It's really good stuff to think with. I also work a lot on scientific and popular narratives about humanity's past and the philosophy of science. So I teach archaeology as well as space-related courses. And I've been working around astrobiology and SETI for nearly 20 years on a variety of themes, including the evolution of intelligence, evolution of humans, issues at the intersection of astrobiology and society, including space ethics, post-detection, societal impact issues, and stuff like that. And I've organized and participated in quite a few AbSciCon sessions and workshops by now, including we did the evolution of intelligence last time. This was in Atlanta, and the roles of social sciences and in astrobiology science. So if you're interested in any of that, come find me virtually. I'll be happy to chat and answer questions. In relation to SETI, I just want to say I do quite a lot these days on post-detection problems, not actually necessarily because I want to, but because somebody needs to. But I really, really emphasize working on the human side of that equation, not the ETI side personally. I personally feel really dubious about the utility of a lot of speculations about aliens. That we can be sufficiently right for predictions to be useful, and I think it's more likely for us to be detrimentally wrong. And in my experience in archaeology, it's really hard to unseat a narrative and rewrite a story. Sometimes you're better off not having a theory at all than trying to undo one in the face of new evidence. So personally, I tend to just hold open that alien space and just kind of say, look, if we don't know anything about them, if indeed they do exist. But I do respect that other researchers have different approaches. And I'm not saying that it's all useless. That's certainly not what I'm contending. I'm just explaining why I focus the way that I do personally. People expect me to do alien sociology, but I don't. I love these philosophical questions about the best ways to think. How do we use the data that we have from Earth to think through possibilities for life of all kinds elsewhere? And how do we do that with maximum wisdom? And this was actually the very first topic that grabbed me when I attended my first workshop at the SETI Institute in 2003. I was just stunned by how differently people in the SETI and astrobiology community talk about humans compared to the way that we do in anthropology. So over the years, I've written a few papers on this, including Social Evolution, State of the Field. And that one, I go into collapse and historical trajectories. And so I mention that because it may be of some use to people who are in this session, if you're looking for something that addresses that topic from an astrobioseti kind of perspective. 10,000 Revolutions being technological. Impossible predictions of the unprecedented, I think, may also be specifically relevant to some of what we're talking about here today. And then a couple more. The most recent one, How Humans Matter Now. So this kind of spells out the relevances of anthropology and archaeology for the new study. How do we best use those data sets? So in my title, I suggested that some where am I now? Here's what I want. Okay, so I suggested that some anthropological lessons learned the hard way may aid astrobiological thinking. Quick definitions here, I'm including archaeology, paleoanthropology, biological, and cultural astrobio. I'm thinking big picture. The hard way, I mean really hard. Anthropologists and archaeologists are frequently heartsick, partly because of the destruction of who and what we study and hold dear. But also partly because of the weight of past mistakes in our settler sciences. Astrobiology is positively restful by comparison, though that will change, of course, when humans start seriously messing up other planets. But on the bright side, we do have this ton of data, a long disciplinary history, subjects who talk back to us, and so we've become quite good at some things recently, precisely because we were so bad at them before. So we're actively remaking the ways that we look at and understand and talk about the history of human beings on this planet. We're really, really kind of living that hard work in our fields. So for the final couple of minutes here, just very, very quick suggestions. First, if you're using human historical and archaeological record for raw material or examples, think through your ethics carefully. Are you sure you're not misrepresenting somebody else's past? It's actually really hard to be sure about that. And if you're using outdated sources, you can better believe that they're not the best of our current knowledge. Remember that the people of the past had agency and free will, and so do we. Easy to elide that. Avoid the fiction of the unified we. Obviously, humans are just biological species. Our cultures, political situations, power, and quality of life vary enormously. It matters when you're talking about the Anthropocene, and it matters for future telling in general. This book will rock your world if you haven't read it. Amplifying what Lucas just said about ascent narratives. The problem with them from the social perspective is not just the undesirable corollaries, it's the accuracy. Humanity's history shows a festival of possibilities, and the unilineal story about hunter-gatherers, et cetera, that we've been told, it's more deeply political and Eurocentric than most of us know. Fantastic book, highly recommend it. So use the historical record to explore the range of possibilities instead, and realize we've lost track of many of them. You're going to use human history in your work. Be skeptical of popular syntheses, which are written by authors working beyond their practical training. I'm out of time. I know, that's terrible. 1 more minute. So look for, wait for, read the critiques by archaeologists, medievalists, indigenous scholars, gender researchers, etc. Reach out to your colleagues, fellow students in those fields, ask questions, collaborate. It's the only way to be on top of the changing best of our knowledge. If you must talk about collapse, read the recent archaeological literature. I can promise you, you won't think about collapse the same way anymore. Please, I beg you, leave Easter Island alone. Question assumptions about your long-lived technological ET civilizations, should they exist, and their degree of pacifism. These assumptions have a lot of implications. They rest on a really wobbly foundation. If you must talk about human-alien contact, be wary of the analogy of the invasions of the New World. Lots to say on that, no time. When thinking about encountering life on other worlds, be realistic about humans' track record with other species in Earth's environments. Remember, human technology relationships are bogglingly complex, often unpredictable. When you just don't know something, consider holding that space open instead of filling it with projections, unless there's a really good reason to fill it. Finally, astrobiology is future-oriented in terms of the discoveries astrobiologists hope to make, the possible results, and the research timelines. And astrobiological imagination propels us to other worlds, other times, many maybes. But there are days when we should be more present in the here and now. And I wonder sometimes if this might be one of them. Thanks.
Thank you, Catherine. That was awesome. Next, we have Carlos Mariscal.
Hey, everybody. Thank you. That was wonderful. I wish I'll talk to you later about writing those down. And I also know the problems of having a research question thrust upon you. So this is the one that has been thrust upon me, the question about how we can know anything about life as we do not yet know it. I'm going to frame it in as the new n=1 problem, but to do that I need to remind you of what the old n=1 problem is, and I believe you will recognize it when you see it. It is, given our single sample size, we are not justified in concluding whether features of life on Earth hold among other instances of life in the universe. This has been said multiple times, most cleanly by Carol Cleland, and we'll talk about that now. Essentially, it's life on Earth all shares common ancestry, and any single individual does not cleanly represent their population. So if you were asked, for example, to figure out what mammals were like based on just a single sample, that is a zebra, you might not capture the breadth, the diversity, the size, the scale, the digestion, any of the features that actually make mammals special. This is Carol's example, and I think it's a useful one. So you might think that stripes and hooves are important, and you might be wrong about those, but you'd be right about multicellularity. You might not pick up on the fact that mammals give live birth and have mammary glands, especially if you have a single zebra to draw that inference from. So I've heard several people say this, most cleanly Carol said this a little while, sorry, I have to go back. We know life on Earth is non-representative. So this is an image of polyextremophile space. That is the pressures, the depths, oh, the timing of these is affecting me, of life as we know it here on Earth. I don't know what I expected to see, but this was a weird shape to see, right? So there's some assumptions that go into the n=1 problem. Namely, that for any sample that you care about, there's going to be one category that it belongs to that's going to be salient and important. In the case of zebras, like it would be mammals. In the case of life, it'd be life in general. I argued against that in print in 2014. The next two, that we would recognize new cases, we saw them as belonging to the same kind, that we would recognize life when we saw it, and that the kind life is held fixed, and we just need to figure out what properties make it up. Those are the questions that those are the assumptions that I'm gonna be questioning now in the new n=1 problem, which I'm going to formulate like this. Life on Earth belongs to and provides equivalent evidence for an indefinite number of broader categories, none of which are non-controversially equivalent to the life category itself. So take life on Earth. You might be impressed by the lifelike behavior that it exhibits. You might think that the cause for that is that it is an evolving by a process of evolution by natural selection. You might think that there's some sort of complex information that it is capturing that we can, that's the heart of life. You might think that there's some sort of metabolism going on. Or any of the other categories we've heard time and again from everywhere. Namely, there's these categories that we think life on Earth belongs to, and some people say, oh, that's just what life is. And we have this debate back and forth, and you debate whether mules can reproduce and whether fire metabolizes. You have this back and forth where people take their preferred view and argue about it. And so I think going back to the formulation, when we say we know life on Earth is non-representative, I mean, the question to me immediately is of what, right? Maybe it's very representative of metabolizing systems, but it's not representative of evolving systems. Or maybe it's very representative of lifelike behavior, but it's not representative of complex information as we would expect to see it elsewhere in the universe. And that, I think, is the heart of this. We had this old problem where we had this example of life here on Earth, and we thought we would go and find the aliens, the Martians, and we'd know what they would look like, and it would question our assumptions, of course. Sorry, the timings are going to be killing me. But the new problem is we know that it has properties, and these properties are essential to any number of categories. But the question is, which category is the one that we care about? So to convince you of this, I don't think I have yet, but to convince you, let's say there's any number of evidence that we could find, any kind of data that we could find, and we can break it down this way. Data where very few people agree, which I think has happened numerous times before. These tend to be dismissed, right? There's a couple of people like Gil Levin thinking that we discovered life on Mars back in the 70s. And the scientific community is a community. We can ostracize people. And so I think that's sometimes when we have cases where only very few people agree, we find it easier just to not talk about some of those examples. The questions that I find most interesting are when some experts agree, and you have these factions forming where you find some muck and people say this is life, and other people say that's not life. If you go to any of the artificial life symposium or origins of life conferences, you'll see this happen again and again, where well-meaning scientists ask the question, yeah, but is it life? This is an open question argument. When somebody says A is B, and somebody can reasonably say, but is A B? That means that there's something not fully captured by that equivalence. So every time people go with their preferred view, and they say, oh, that's just what life is, and other people say, well, but is it? That shows that there's these factions that can easily form. The third case is the case that everybody would love, right? The case where you just find an alien that happens to look exactly like humans. But that actually gives us too little information. It doesn't help us decide the problem cases later on. Ideally, that's what we find every time. We will always, it'll just bunk us over the head. We'll see rabbits on Mars or under the water in Europa. That'd be problematic. But I don't think that that's what we should expect. Instead, I think ways we can avoid this is by either voting or just everybody that we disagree with dying mysteriously. So let's focus on the first one. The hope is that life is going to be something like chemistry. Biology is going to be like chemistry. The ancients knew what water was. They knew what gold was. And then came modern atomic theory, and we supplanted this concept of gold, this yellow malleable substance, with an atomic number, and we said, this explains all of the things that are interesting about the things that the ancients were calling gold. So we said, no, gold just is atomic gold. Although I've seen gold a couple of times in my life, I've never counted the number of protons in a sample, right? So there's a sense in which it's actually not very useful. There's another sense in which there was a choice that chemistry made, and that choice, you can see it in the periodic table. The periodic table is this masterwork, this ideal. If a science could have something like the periodic table, then it divides reality, we think, in one of the best ways, namely by number of protons. About a minute. But you could have divided it in terms of isotopes or ions or any number of other things. You could have divided it in terms of the pressures that you would expect the elements to see and the behaviors they would exhibit. Elements are posits, essences are posits, they're theoretical posits, and in chemistry we convinced the public that chemical elements just were the elements we cared about. And I don't expect that we will see that in biology at all, because we already have the problem cases, the cases of RNA worlds, of viruses, of prions. We already know that factions form. We already know that we're not going to find the neat case that there's stable property cluster that everybody will be happy with. So let me just wrap up very quickly. There are an indefinite number of answers over what the category life is. Any evidence speaks to an indefinite number of categories. What is life is a decision. It is not a discovery. Thank you.
Our next discussion will be David Deemer speaking about urability remotely.
In 1993, Jim Casting and his co-authors came up with a concept of habitability and the habitable zone. And that's kind of, those words have grown into our language and very commonly used because they're useful. However, habitability does not necessarily include the origin of life. And my co-authors and I have discovered that a word is missing. And the word that we're going to try to use among ourselves, and maybe other people will find it useful, is urability. Now, urability has the combining term as original, earliest, primitive. And Ernst Haeckel, way back in 1860, used that same combining term to describe earthslime or primordial slime. So if you look over at the image on the right-hand side of the screen, here's a primitive planet. There's no life there. Is it habitable? Probably. It's got liquid water there. Depending on how long that liquid water lasts on the planet, we would call that a habitable planet. But can life begin on this planet? That involves a large number of other sorts of considerations. So let me just tell you a bit about urability. It has to do with conditions that allow life to begin. So down below, you see some planets that these are exoplanets. They're artist representations, of course. We can't really see them this way, but these are in the habitable zone around their stars. So if water was there, it would probably be liquid water. Could life begin on such planets? Not unless there are conditions that allow them to be errable. So let me illustrate that with this little simple diagram. On the left, you see a flask with a bacterial culture medium in it. If I add one bacterial cell, a live E. coli cell, for instance, and come back 2 days later, it is loaded with billions, if not trillions, of new cells. So certainly, there's no doubt that that is a habitable medium. But if we just let it sit there year after year, Louis Pasteur showed us long ago that it was no life could begin under these conditions. We would say that that is an inurable solution, just as certain kinds of planetary conditions would not be sufficient for the emergence of life. So what we're doing now is to try to sort this out and see what we can put together as a way to define this word by the kinds of conditions that are going to be required for life to emerge. So let's just take some dry sand. I think everybody will agree that that's inurable. Life is not going to begin in dry sand. Let's add some water to the dry sand. Suddenly it becomes habitable because there are certain microorganisms that can make do just with light as an energy source, as long as some minerals and certain nutrients are available, but certainly would not expect life to begin in wet sand. Let's add a mixture of organic compounds, such as we might extract from a carbonaceous meteorite. Well, this is getting more complex, but if the organic compounds are at chemical equilibrium, nothing would happen, no matter how long we waited. So we have to add something else. And of course, you guessed it, we must add energy to move those organic compounds away from equilibrium. Now something can happen, but it has to be a relatively specific reaction that happens if we're on the way to life as we know it. And that is the energy source must be used to drive polymerization of some of those compounds that can be monomers. This would be amino acids, and we know that those are in the Murchison meteorite, for instance, so they would very likely be available on the early Earth. We also know that the bases, nucleobases of DNA and RNA, some of them at least are in the Murchison meteorite and other meteorites. So it's likely that there might be compounds able to polymerize into peptides, short peptides, and oligonucleotides, short strands of DNA or RNA. Then there's got to be one more step, and that is that if we're going to have cellular life begin, there has to be a way to encapsulate it in lipid boundaries, such as what we call liposomes or lipid vesicles. Furthermore, you've got to remember that if you have a milligram of lipid and turn it into small lipid vesicles, we have populations of what we call protocells that have encapsulated some of the polymers. Every protocell is different at this point from all the rest because there's been nothing directing the kinds of polymers that they would encapsulate or the sizes of the protocells. So something else has to happen, and that is we have to add selection. There must be things happening in the environment that will select more robust protocells or protocells with catalytic activity, for example, or pigments that can pick up light energy and do something with it. So selection can begin in populations of these protocells, and then we would have the first steps of evolution. At this point, if these were on a habitable planet, I would say that the planet also has the conditions required for errability. Well, this is pretty broadly based sorts of things. Let's go to a little bit more specific considerations, let's think about the sorts of Goldilocks that we would want to have available. And those can be illustrated by these strips of colors that you see. On the left, you see a strip vertical having to do with temperature. It's if the temperature is frozen, life could not begin in ice. If the temperature is so high to have the solution boiling, that would be difficult to have the bits and pieces of life come together in such a way as to get a living system. Same is true of dry and wet, and also light and dark. If there was no light energy, the organisms would be stuffed at a very primitive level. There's too much light energy, such as UV light, that is damaging to the compounds. So these three strips come together in such a way that there is what we call an errable center. And that is a sine qua non for errability, is to have those centers show up. Off to the right is a number of specific ionic solutes. You can go all the way from saturated to dilute solutions and make the same sort of argument. So let's now go to the sorts of things that we can add to planets to let them have errability. There are two kinds of factors, geophysical and geochemical. I can only touch on a few of these in the time that I have. So let's just go down a couple of lists of geophysical. Of course, the size of the planetary body is going to be part of it. We also have to think of whether the planet is rotating or not. That is going to have some effect on errability. Presence or absence of a moon, in my opinion, probably not essential. Mars doesn't have moons, but I think that early Mars, as you will see, was probably errable. Planetary core composition, that is going to be important because that can drive volcanic activity. And that in turn can go a long way toward making a planet errable. I'm just going to go through the rest of these quickly, get down to geochemical activity, which is the next slide. These are a little bit more complex. And again, I have to go through them rather quickly to finish up. The atmosphere really can't have molecular oxygen as we do today. Oxygen's corrosive of the kinds of molecules that we'd want to have there for life to begin. The water, if it's going to be a reactant, has to be within temperature ranges that support prebiotic reactions. The ionic concentrations have to be moderate. They can't be too salty brines or completely diluted. There has to be, of course, elemental cofactors. There must be intermediate pH ranges, and there must be a continuous source of organic compounds made available. So the rest of these I'll quick through because I want to get down to Mars as an example.
David, we need to wrap up.
Okay. Mars began errable, but became inurable as the atmosphere was eroded. The Earth began errable, but oddly enough, became also inurable. Darwin said it best, the life on Earth has become so complex that it would simply eat the compounds required for the origin of life. Notice that this paper is coming on astrobiology in the next few months. So in it, we give the details of the argument I've made here today. Thank you for your attention.
Wonderful. Our next talk will be Bonacorsi.
I probably would just go there. Oh, hi. So let's go forward to the next slide. So we are talking about terrestrial deserts are expanding biome due to the enhanced anthropogenic and climate factors. So there's been tons and tons of paper talking about this, in particular comparing present-day bioclimatic information between area regions like the Mojave Desert as a part of the American Southwest and Atacama Desert. They would provide information and prediction about the onset of hyperarid conditions in the American Southwest over the next decades. And there's a lot of talking about that in the IPCC 2022, the sixth one, and it's just humongous document, and you can browse by yourself. The Mojave Desert is a core part of the American Southwest and Southwest, and encompass California and Nevada, and is chain bound by the Sierra Nevada, so high elevation, and because a set of parallel chains of mountains, it creates a rain shadow, exactly also as it happens in the Atacama. This is why it's a arid desert. And so you can see here the beautifully colored picture from the data basin, which is a nice website resources where you can map maximum temperature and rainfall and aridity index. You can really see that the Death Valley, that's kind of super color things, is where we get the highest temperatures. And also we have a high aridity index beside the Sierras, so it characterizes the Death Valley that's within the Mojave Desert, not just as a arid site, but just hyperarid site, which is probably might not is not very very well known. So we have been over the past 14, 15 years setting up rainfall measurements using Hobo RG3 rain gauge as a tipping bucket, allows for the continuous monitoring or rainfall, and we have been setting up at elevation between 650 and 1,000 meters. Why? Because this is the mountains, this northern part of that valley. So it's kind of sensitive region where to look at this variation. It's also not very well known in terms of the rain precipitation. So this is my favorite post-COVID curves, where we were able to recover 2 years of data just in time. And you can see the blue curve, which is the cumulative rain. And we can see that 2020 was a super wet year, and then the blue curve becomes flat, which means there's not been rain enough. So there's about more than 20 months that qualifies almost like in one of the longest period that, of drought that we have. So here, so you can see the data set we gathered from 2004 to 2022 of the monthly distribution rain, where you can see that typically in the Mojave Desert, in the Death Valley, the rain is concentrated between October and February, and then we have a summer monsoons. But you can see that toward the more recent times, we have an empty space, like blank spaces, just because we're getting lesser rain, both in summer and in winter. Actually, sometimes more in summer, depending to that the years are wet or dry. So, so this is local data, and we can see the total annual for the same period of time, and we have the dot lines that clearly show there is a downward trend of we get the minima of in rain get lesser and lesser over time. And we can also look at the big picture, the climate regional data, so it matches what we see locally, okay? And it's interesting to know that wet and dry cycles are a common feature of Earth climates, but yet the drought cycles observed over the past 20 years include dry years with lowest minima. This appears to impact the Mojave Desert, by default the southwestern United States, and this translates in some effect and some impact on the entire ecosystem, from what we can see, plants and vascular plants, to what we cannot see. So it's getting hotter. The same data set from 1895 to 2020 can clearly show that is this trend about 2-3 Celsius degrees. That's for the Mojave region, the entire regional data set. And then you can see the kind of like spiraling up, the curve. Also matches with anecdotal observation, which means anecdotal perceived by people when you talk to the people that's been staying long enough in that valley, that the summer temperature, the night summer temperature, where part of those minima are becoming hotter. So just basically the ecosystem doesn't have even those 3 hours of reliefs where everybody out, eat and feed, and that's possible to continue life in a desert by adaptation. It's very interesting to see how the data set can match also anecdotal observations beside the data set. And then we can also see like the last 7 years at global level have been the top hottest. So this was a breaking news, like everything is really becoming hotter. We can see from the local data, the sub-regional data, regional data, and global data. So what is the impact on life? Because this is what we really care most, is that you can see here all those pictures from that valley. So that valley is arid, but within that valley, we have a hyperaridity gradient. So we can see happy plants, sad plants, dead bodies, biological matter will be never recover. And if you stay long enough, you walk for 15 years over there, you can perceive like the change as we speak. So plants die, never recover when you get the wet year back. To understand the impact of the arid to hyperarid transition on the future of Mojave Desert, we can look at what's happened along the latitudinal precipitation gradients across the Atacama Desert. So as you know, the Atacama Desert has been defined as Mars-like soil because in the northern part, soils were analyzed and bear the very, very small amount of biologically active microbes. So we can see that along the rainfall gradient goes from south to north. We can see the reduction in vascular plant density first. In terms of desert ecosystem, we have a shift in terms of less and less shrubs and insects, in going toward the hypolytic algae and hypolytic cyanobacteria to places where, going farther north, where the biology wins, and then toward to lesser than -2 millimeters, the biology lose. So this is what is thought, okay? But this gives us a window in what could happen when the aridity index drops. So it's an open portal in the future. So here's the microbiomass in that valley versus the Atacama. So Atacama in the hyperarid can go from, this is ATP-based, only active cells, let's say 10 to 2 to 10 to 3 cells per gram. Then you see that valley, the biomass, microbial biomass can go from 10 to 3 to 10 to 6 cells per grams. In barren volcanic materials and vegetated clay-rich or grounds still vegetated, still arid. And that valley is 50 times wetter than the hyperarid core, the Atacama Desert. It's less than 2 millimeter rain. So, okay, conclusion. In the context of American Southwest climate evolution, climate models predict increasing aridity of already arid regions. That valley is already one of the hottest dry places on Earth within the Mojave Desert and is in climatic and member for the entire American Southwest. Our 2021 precipitation data from 2 northern Death Valley stations are consistent with the Western Regional Climate Center precipitation data, highlighting increasing arid conditions. The acidification seems driven by increasing global air temperature, within the last 7 years, ranked as the top 7 hottest of the century, higher minimum temperature, hotter summer higher than 35 centigrades, decreasing rainfall events, supporting long-term desert vegetation. And this can affect abundance, growth, diversity, and distribution of microorganisms. This is very important, a level of soil and productivity over time. So, and bottom line, the north-south precipitation gradient across the Atacama Desert represent a bioclimate analog for the hyper-arid transition in the American Southwest. How much time I have?
That was it.
Oh, okay. I was about to traumatize everybody. So
if you want 20 seconds.
Okay, 20 seconds is that I'm going to traumatize you with additional slides. This plot is becoming this. Ta-da! After flooding in 2017, the Atacama Desert probably is no longer Mars-like. And I'm going to traumatize you even more. Bad news for astrobiology. Well, good news for another type of astrobiology is what is happening. Flooding in Atacama, 2015, 2017, 2019, and 2020, and counting. So these are 500 years events that happens basically every year. And these accounts why we've been seeing those peaks in the last, astrobiology-driven work that we've been doing at Atacama. So that's what's happening. Thank you.
Wonderful example of recent trends that we can trace into the future. And we have Michael Wong.
All right, hello everyone. It's good to see you all. Thank you for organizing, Lucas, this really important and fun session. So today I'm excited to tell you a little bit about a paper that my colleague Stuart Bartlett and I wrote and recently published in JRS Interface called Asymptotic Burnout and Homeostatic Awakening, a New Solution to the Fermi Paradox. And don't worry if these terms are unfamiliar to you. We literally made them up for this paper, and I will explain them to you in the next 10 minutes. So, but let's just start with one that you probably have heard of before, the Fermi Paradox. This is stated as in a universe that seems amenable to abiogenesis and the evolution of life, why haven't we seen definitive evidence of extraterrestrial civilizations? This can be sometimes couched in the framework of the Kardashev scale, and the question can be posed, why don't we have any evidence of type 3 civilizations at the galactic scale in our galaxy, or from, as far as we know, in any other galaxy that we can observe? I think that there are two main things missing to this logical framework. The first is that evolution, we now know, is not only a gradual process, but it is punctuated by major transitions. And two, that crises or singularities may occur at the scale of cities and planets that necessitate another major transition. And I'll explain what I mean by singularity in just a sec. But to me, the Fermi paradox appears as a paradox because there is an implicit assumption that the trajectory of quote-unquote progress can be extrapolated from the past, but this may not be so. Okay, let me talk about the singularity. So this comes from research thinking about cities as sociological organisms. So there's been well-documented research showing that socioeconomic metrics, patents, GDP, R&D, total energy usage, etc., scale superlinearly with city populations. So in log-log plots, like I'm showing you here on the left-hand side, you see these linear trends, and they have a slope of greater than 1, something around 1.15 or so. And this superlinear scaling has been attributed to the social nature of cities, that social networks are driven by information flow overlain on top of energy and material networks. And so there's an analogy to be made between cities and stars. From astrophysics, we know that stars are basically nuclear reactors, where the larger the star is, the faster it is able to sustain nuclear reactions, the faster it goes through nuclear reactions. The same thing for cities. The larger a city is, the faster the social interactions in cities are. In fact, it's been shown that people actually walk faster in larger cities. Research by Betancourt et al. Have shown that superlinear scaling can drive singularities. And so by singularity, this means an infinite amount of n. N is just something that scales superlinearly, population or energy usage, in a finite amount of time. And obviously that is not possible, that's not sustainable or reachable, but you can push back this singularity or crisis further and further in time through innovations that reset parameters in this general growth equation. Now, the time scale between necessary innovations to keep pushing yourself back further in time in the future before you reach a crisis will decrease as time goes on. So the pace of innovations must increase. Can we extrapolate this to the planetary scale? I think that we might, because we are currently undergoing a major transition in information processing right now. And we can see the evolution of life as a series of major transitions, information processing happening at the chemical scale within our genomes, then in the neuronal architecture of our brains, and finally now in this distributed information processing global scale through our technology, or what Caleb Scharf might call the dataome. So technology has enabled us to literally sidestep the physical limitations of human social interactions. And remember that it's the social interactions that seem to drive the superlinear scaling of cities. And so therefore, I think that a planet need not physically be one global city for a planetary civilization to behave like one. In other words, you don't need to have Coruscant, for our Star Wars fans in the audience, for a planetary civilization to scale superlinearly. And so the asymptotic burnout hypothesis is this, that a planetary civilization optimizing for growth and productivity will march towards a singularity. At some point, it will no longer be able to be sustained by the resources that it can collect because of this singularity, infinite amount of energy usage in a finite amount of time. And it's a problem that these cycles of innovation keep getting faster and faster. But not only that, the magnitude of disruptive fluctuations that the civilization can impart on itself grows as energy and information harnessing powers grow. So our unlocking of fossil fuels has induced climate change. Our unlocking of the power of the atom has induced the potential for a nuclear disaster. And our unlocking of, or the invention of, the internet and our distributive cognitive processes through our technology invites what I call a disinformation catastrophe. So is there a way out of this? We propose a hypothetical scenario called a homeostatic awakening, which is that prior to burnout, a planetary civilization has the chance to realize the trajectory that it is on and effect some kind of conscious adjustment to it. On Earth, this awakening has required a cognitive horizon that only emerged at the scale of civilization. So we're kind of in a catch-22 here, where you kind of need to be a planetary civilization before you can realize that civilizations tend to set themselves up on these superlinear trajectories towards burnout. Therefore, the window of opportunity that a civilization may have could be very short compared to classic geological and evolutionary timescales. And also the requirements for rewriting the underlying dynamics of society in this way are highly unknown because we haven't done it yet. Are there reasons for optimism? We outlined several in the paper. I'll give you one here, which is that previous evolutionary adaptations show that homeostasis can be achieved when new levels of organization emerge. So for instance, bacteria can do this thing called quorum sensing, which is they can understand that they're in that the population of cells around them is very dense, and that will actually trigger a change in their gene expression that changes their behavior as a result of living in a very dense environment. Multicellularity, of course, is a very classic example of how homeostasis can be achieved at new levels of organization. And there's been very recent research into how cancerous cells can be normalized through bioelectric signaling in the organism. So I wonder, is self-awareness-driven reprioritization towards homeostasis the next transition that life takes or must take after civilization as we know it? So in graphical form, we hypothesize this, that after the origin of the dataome or the onset of civilization, civilizations will increase in population size and either follow a burnout trajectory after they reach this burnout horizon or realize that they're headed towards that and then consciously adjust their path towards homeostatic reorientation, meaning that the volume of state space that belongs to these hypothetical type 3 civilizations is relatively difficult to reach. So we think that this constitutes a novel solution, or quote-unquote solution, to the Fermi Paradox because previous solutions often invoke bottlenecks that are probability-based, basically equating a low, very, very low value to a Drake equation parameter. So maybe the origin of life happens 1 out of 1 to the power 100 times, or the origin of complex life, or the origin of intelligence or civilizations is just super, super rare. But our proposal is different. It's that maybe there's an inevitable barrier emergent from the dynamics of energy and information flow within a living system that civilizations will either meet and faceplant into or realize they're headed towards and learn to redirect themselves around. So the implications of this, one of the implications is that the expected lifetime of civilizations might be bimodal if this hypothesis is borne out. Actually, I should note that this whole thought process was spurred by a panel that Bob Hazen invited me to, all about this expected lifetime of civilizations. And I started thinking, what in the world can I possibly say about this? But anyway, that's an anecdote that's probably too long for this 10-minute talk. So bimodal distribution to L, we would expect, if this hypothesis were true, that you would have a pileup of civilizations that have collapsed due to burnout, a pileup of civilizations that have achieved homeostatic reorientation, and virtually nothing in between. In fact, Jill Tarter proposed to us that maybe it's the detection of extraterrestrial intelligence that is what gets you from one hump to the other. But I think there might be a catch to this, which is that civilizations that are about to burn out may be the easiest to detect because they are dissipating energy at a wildly unsustainable rate, whereas those that have achieved homeostatic reorientation may be indistinguishable from nature or very difficult to detect. So I'll leave you with my conclusions, the definitions of these hypotheses, asymptotic burnout, homeostatic awakening, and how this may constitute a novel solution or resolution to the Fermi paradox. I want to reiterate that this is just a hypothesis. We're not claiming that this is necessarily true or fact, but this is just adding another idea to the table to spark discussion and introspection, especially about whether or not we are on this kind of trajectory and how we can determine if we are, and what to do if we find that we actually are headed on a burnout trajectory. I also want to just leave you with this thought, because this session is titled The Future of Life, that if we look backwards at the evolution of life, we realize that life has gone through many major transitions in complexity, organization, units of selection, and information processing, and that we're going through one right now. And so it worries me a little bit to talk about extraterrestrial civilizations colonizing the galaxy in this unsustainable manner when that's based on simply that that's what our ancestors have done here on our planet. Thank you very much.
Awesome, thank you. And our next presentation will be by Kat Gillen.
Hello, I'm super excited to be here. So my name's Kat Gillen. I'm from Durham University. I just started a PhD there as part of a project called the Eureka Project, which stands for Exploring Uncertainty and Risk in Contemporary Astrobiology. So today I'm going to talk about the rather salaciously named talk, How to be a Rational Astrobiologist. So I will be talking about a particular type of bias that exists widespread in the psychology of reasoning, so that's called my-side bias. And I will discuss, as there's evidence that this might exist in astrobiology, and I'll discuss some of the implications of this. So first of all, biosignatures are inherently uncertain indicators of life. So even if you get the kind of smoking gun biosignature, like an oxygen-methane disequilibrium around a planet, you still wouldn't change your probability that there's life on that planet to 100%. So there is a need for a mechanism for updating your prior belief based on this uncertain information, and usually Bayesian statistics is suggested to do this, and it's widely explored in the literature. Like the main benefit of this, or one of the main benefits, is that if you do follow Bayesian statistics, you'll be protected from violating the axioms of probability. So that's great. But the question remains of whether astrobiologists do actually update their beliefs in compliance with Bayesian updating. So, in a paper released last year, Baines and Pekowski attempted to answer just this question. So Baines is one of the co-authors for the Greaves et al. Paper detecting phosphine in the cloud decks of Venus. And so interestingly, they sent out a survey before the release of this paper, the Greaves et al. Paper, asking a bunch of astrobiologists and also researchers in related fields what they thought the probability of finding life on these 5 bodies were. So we've got Enceladus, Europa, Mars, Titan, and Venus. And then that's what we've got in the first survey there. We've got the results. And then the paper came out, and then they sent out a second survey asking the same question. So yeah, we can see that there's a statistically significant change for Venus. Just looking at the first survey, the respondents were super skeptical at first. Nearly half of the respondents said there was a 0% chance. And this has kind of trickled up with the second survey. So there has been an update in the respondents' probabilities for life on Venus, presumably due to this paper that's come out. So yeah, is this a Bayesian update though? Can we say this fits within a Bayesian model? So that's what they then explored in this paper, and ultimately they concluded no. So yeah, Baines and Pekowski did a principal components analysis, which we've got there in that graph. And basically, they took 4,000 combinations of prior probabilities to allow for this whole range of different priors, and saw whether any of those would fit within a Bayesian model for what the respondents said, and they found that no. So the blue dots, they are the Bayesian models, and the red dot there, that is the what the respondents of the survey came out as. Okay, so interestingly, they did find that if you artificially double the 2% bin, so I'll just go back. Like if you look in the second survey, the 2% bin is that kind of orangey yellow one, then you do bump up the results to within a Bayesian regime, but this is just artificially done. So ultimately, they found that the respondents were not increasing their credence enough based on the apparent biosignature. So they concluded that they weren't that they weren't Bayesian, but they were nonetheless rational. Okay, so this is something I would now like to challenge, just that second bit. So I propose instead that, yeah, indeed, the astrobiologists did not fit within a Bayesian model, but they might instead have been exhibiting my-side bias. So my-side bias, it is a well-documented phenomenon in the psychology of reasoning. It exists in many fields. And just in short, if you're my-side bias, then if your probabilities exist towards the extreme, so maybe you strongly believe something or strongly don't believe something, then you will selectively weigh evidence. So more specifically, if you really strongly believe something and you hear evidence that says otherwise, then you'll see that as a bad argument and you'll underweight that evidence. Whereas if you hear evidence which confirms your existing prior, then you're going to overweigh that evidence and sort of double down on your beliefs. And then, yeah, if you just have 0.5 probability, you won't exhibit my-side bias, and it gets stronger towards the extremes. So just looking back at the data then, if we just see if this does indeed more accurately fit the data. So yeah, we can see with the first survey, the respondents were very towards the extreme. Like most people said 0 or 1% chance of finding life on Venus. And so my-side bias will predict that if these respondents hear information that says otherwise, they will instantly view that information as a bad argument, and so won't incorporate that in a way that Bayesian statistics would compel that they do. So therefore, they wouldn't increase their credence enough, which indeed was what the Baines and Pekowski paper showed. So that's great. Okay, so if indeed astrobiologists are exhibiting my-side bias, what would be the undesirable implications of this? So the main concern with my-side bias is that updating is non-commutative. So this just means that it matters what order you learn evidence in. So I've just got a sort of figure here, whereby say you start off with a probability of 0.5, and then you hear information which bumps you up, you will then become biased against information that's going to bring you back down. So if this was just a Bayesian agent, they would end up back down at 0.5 for their final posterior. But yeah, a my-side bias agent, we get this divergence, because conversely, if you heard the negative information first, you become biased against the information that brings you back up. So yeah, you get this splitting of views. And it depends on what order you hear your evidence in. So this might have already come into fruition. So there was, in the 70s, there was a lot of buzz about finding life on Mars. And then the Viking lander mission came back somewhat negative. But then in 2006, there was this evidence that the TVGC-MS experiments were not actually sensitive enough to pick up on some of the organic material. So they had taken sample soils around Earth, which are known to contain organic material, and it did not pick up on this. So this should somewhat negate some of the results from the lander mission. But yeah, agents might still be biased against that. So it is very important to just be aware of these biases in astrobiology, particularly also because in astrobiology you often can't take repeat experiments for the same data point. So you can get entrenched and it's difficult to recover from initial bad information. Okay, so just to conclude, so there exists evidence astrobiologists, like many other researchers, exhibit my-side bias, and so this has some undesirable effects, predominantly due to the non-commutativity of evidence. So that puts a bias on early evidence and can lead to a lag in theory and belief change. So in summary, agents should strive to comply with the orthodox Bayesian statistics wherever possible. And yeah, that was my talk. Thank you very much for listening.
Thank you.
Thank you.
I think we have time for one question for Kat Gillen because she was so succinct. Does anyone have a question? And I'd invite the panel folks to come up and join us while we take that question.
Hi, Cole Mathis, Santa Fe Institute and Arizona State University. Really interesting talk. I'm curious about the analysis that the Baines paper did on the sort of Bayesian update, and if they were looking at the beliefs of the community or the individuals, and if they were looking at the community, were they averaging the beliefs of the community or sort of stacking, or if there's a difference between those? I realize it's not your paper, so it's too technical.
Yeah, so I believe that they took an average as the community as a whole, which is, you know, you can't then extend that to saying individuals aren't being Bayesian. So yeah, that is a good point.
Thanks.
Okay.
Awesome. Thank you.
Thank you very much.
Probably not. Oh, go ahead.
Should I just get it?
No,
Oh,
please.
No.
Oh, so a special thank you to all of our speakers who spoke very, very quickly so that we would have a little bit time for some more open discussion. The motivation for this session was this idea that as astrobiologists, we say that we study the origin, extent, and future of life in the universe. And what exactly does it mean that we study the future of life in the universe? What is the methodology behind that? How might we do that well? And so I've asked a few folks who have been thinking about this for quite some time to give us brief reflections, but then I would like to open things up to a broader discussion. So we have met Carlos Mariscal already. We also have Lynn Rothschild, who is in synthetic biology at Ames, and Rocco Mancinelli, who is editor for the International Journal of Astrobiology, both of whom have been thinking particularly hard on this question. So I'm going to start by asking our panel to just very briefly say what interests them about this question and one example of really good work that has been done on this in the past. And Catherine remotely is on our panel as well, so I'll prep her as soon as they're done. We'll go to her. Carlos.
Hi, yeah, so it's interesting to talk about the future because one of the things that interests me is thinking about life as we don't know it, right? So universally, I'm interested in life elsewhere, not at any particular instance. So I want to think in terms of the entire range, the entire lifespan, right? Examples of things that are going on now that I find particularly insightful and interesting are the work that our panelists are doing, of course, and the work actually several people in the audience, Betul, Sarah Walker, several other people, William Baines also. I think there's lots of people that are really interested in not just where life goes from here, but where life would go from like the entire range of possible origins. So I'll just say that very quickly and pass it over to Lynn.
Thank you. I really believe in many ways that the future of life is the most important of the three major questions of astrobiology because it's the future, it's where we're going to be. And to some extent, it's the mirror image of where do we come from. And astrobiology, I think at its core, really, it looks at that interaction between the physical and the biological world. And as I was preparing last night, I did remember in one hard flash that I had been in a documentary with the very cheerful title, Death of the Earth. It was Naked Science. It premiered March 11th, 2009. I played myself. And one of the reviewers said it was a depressing program on the basis of which I firmly decided not to live another few billion years as it's not worth it. And that was my father. So they got worse from there. Anyway, I cannot tell you how depressing it is to have very cheerful people calling from London at 7 in the morning and saying, exactly what year is all life on Earth going extinct, Dr. Rothschild? So let me give you just quickly the take-home message there and then end on an optimistic note. And that is, I've always believed that astrobiology really isn't the next 5 or 10 years. It's a much longer time scale because we are looking at planetary phenomena. That being said, climate change is occurring much more quickly than we would have expected. And this involves not only changes in the atmosphere and the temperature and the rainfall, but also ocean circulation and so on. We can always have your odd event like a supernova or an impactor showing up that we hadn't expected. We could have things like life detection. We've got the robotics. We've got other, sorts of things happening. But we have planetary factors even within the next 5,000 years. Then you start to move to the 250 to 350 million year time zone, and you're starting to look at new supercontinents, which changes climate dramatically, and then a breakup. These things happen periodically. 600 million years, you're now starting to talk about not having enough carbon dioxide for C3 photosynthesis. By 1 billion years, solar luminosity is about 10% higher. The atmosphere becomes a moist greenhouse. And then you get the big event of, biggest one of them all, 1.5 billion years, death of all life on planet Earth. And so you're not really going to care that in 2 to 3 billion years, Earth's magnetic dynamo may cause the speeding loss of volatiles. By 2 to 5 billion years, the moon, as it's continuing to go away from the Earth at about 4 centimeters a year, just slightly less, may reach a point where we've ended up with a more chaotic obliquity, but it's not going to matter because life will already be extinct. And by 4 billion years, Earth will be more extreme than present-day Venus, which is a hellish place to begin with. By 7.5 billion years, the Earth may well be absorbed by the sun, but it's already going to be a red giant. And before that, in about 5 billion years, the Andromeda and the Milky Way galaxies will start to collide into, and these were my new vocabulary words last night, into the Milkomeda or Milkdromeda, it will be called. But at the risk of having the most depressing talk that has ever been had in an AbSciCon, I want to end on a positive note, and that is to go back to my original point, and that is that the future of life is to some extent the most important part of astrobiology because we are here, we care, and we can actually change this. And this is going to sound crazy, but I actually don't believe that any human is going to want to be the last one to turn off the lights, that evolution works on self-preservation. So there's certainly the possibility of going forward to other planets. I actually personally believe that we're going to start to shift planet Earth. Maybe we'll have the technology to reset the sun, but maybe we'll just end up with spaceship Earth. Maybe we'll be picking up our water from Europa and more organic carbon, maybe some from Ceres on the way out to Europa and then on to Enceladus, and maybe we hang out there until we reach the red giant phase, and so on and so forth, so that we don't even have to worry ultimately, if we have the technology, about the end of the universe, which will be either the big crunch or the big rift, depending upon which category you're in. So I do believe that we're sort of like A Christmas Carol, where Scrooge at the end sees the future and he realizes he can do something about it. And people ask me, well, how do you plan to do this technologically? And my answer is, I can't solve all of the problems for mankind. But I do believe firmly that we will do everything we can for technological solutions, because it's just not in life as a whole, and certainly not in humankind, to be the one to turn out the lights.
Thank you. Thank you, Lynn. Well, I'm going to take not necessarily a happier turn from what Lynn said, but a shorter term sort of time on what Lynn did say. And that is, I think that the future of life has been given short shrift in the astrobiology community. We don't hear much about it, especially the future of life on Earth. We hear about, okay, we're going to go to Mars, or we're going to make settlements out there sometime in the future. But what about today? What about what's happening today and the future of life today? I think we can all say, all right, that we all know that what is astrobiology? Astrobiology brings together the various different disciplines, and we gather data. And I think one of the things that it is critical to astrobiology and understanding astrobiology in life is that astrobiology is really inextricable. The study of astrobiology and life is the study of the environment and life together. In other words, life and its evolution
and changing environments are inextricably entwined together. All right, so since we know that, then what can we do to really study it? And we haven't really done much to study it all together. And I think right now, without being too depressing, is a great time in which to actually study this together, because right now we are going through rapid global climate change. I think we can all agree upon that. And so if we have this rapid global climate change, and we have several fields of biological systems that we're studying that look at what's going on with species extinction, changes in habitats, changes in niches through time, that one of the things we should do, and we were asked actually to say, what should we do about studying the future of life? One of the things we should do is we should bring together global climate change modeling, and the modeling that's done at the ecological and ecosystem level, so that we can really understand better what's going on with how the environment and life is changing for the future. So it involves not just modeling, but it involves gathering real data to feed into those models, so we have some idea not only of what's going on in the future, of what we may be able to do to actually take control of it again. I once heard a talk several years ago that someone said, the life on Earth began as a microbial world. We have now gone through several changes and evolutionary processes where we have multicellularity. We have a diversity of life that's almost unbelievable. However, with global climate change and the changing environment and the changing solar system, we are destined to become a microbial world again. If you look at what Lynn said, and we do take some of these changes and we do something about them, maybe we will stop becoming a microbial world again. The other thing I would say is that I think now is the time for us to really understand what happens, and we can take this data with global climate change and modeling of ecosystems and bring it together to really set a course and a path that will not lead to our extinction. With that, I will end.
Excellent. And a couple quick words from Catherine, and then we'll open things up.
Yeah, I will keep it quick. So yeah, I'm not worried about the 1.5 million year horizon or the milk dromeda personally, just because my brain is not large enough. Lynn's brain is way bigger than mine. I do worry about the near future issues, like Rosalba was just discussing, and of course, the importance of adaptation and resilience. There's kind of one thing that I can add a little bit to what Rocco was just saying, with which I firmly agree. I'm very concerned about biodiversity collapse, because that's something that we haven't seen before on the scale that we are seeing. But I do take some consolation in the archaeological work, which shows humanity's long history of resilience and adaptation to local climate catastrophes. And so I think, you know, we do have this capacity within us, and I think that is some consolation. Whether or not we're able to coordinate on the kind of global scales that are necessary, you know, remains to be seen. But anyway, interesting days ahead. One thing I would just add, though, to that is that I'm not sanguine about the kind of Planet B plans or thought stream that runs through some space-based biology work. It's a source of some concern to me. I'm not sure that you know, the idea of a backup plan with humans off-world is particularly viable, and I worry about it diverting attention away from the proximate concerns right now. I would love to hear a couple things from Lucas if he has anything to add, as well as from the floor.
Thank you. So I think just sort of to wrap up what people have said, there's a whole lot of passion about what we should do in this area. And hopefully, Kat's talk has convinced us all that the more passionate we feel about something, the harder it is for us to be rational about it. And I think that as astrobiologists, as people who really are committed to this study of what it means to be alive at the intersection of chemistry, biology, geology, astronomy, including the including the social sciences and the humanities inputs as well, that we're in a unique place to speak on this question of what we can do now and exactly the nature of the problem. The extent to which we can do that dispassionately, I think, will be reflected in the extent to which we are trusted by the general public to do so. And so I think that we have a particular obligation to tie together really the science and other academic insights we can bring to the problem. So the reason that I'm really committed to this is I think that we have not only the talents, but the platform to speak publicly. And with that comes a great responsibility to be mindful of exactly where information is coming from, when it's coming from the social sciences, when it is being driven by the astronomy, when it's being driven by the biology, and sometimes when it's being driven by our own personal biases. So, I am sure there are people in the audience who would love to make a comment. We have a short period of time, so please connect with people around you and try and make a brief comment if you can, so we can get input from a lot of people. Please.
Can I just,
Hi, yeah, Micah Scheibel,
a brief remark, and that is, there is nothing that we should be more passionate about than the future of humanity. We should be passionate about a field. It's the individual solutions that we need to be rational.
Sure. I totally agree. Please.
Hi, Micah Scheibel, Georgia Institute of Technology. Very interesting talks and statements by all of you. I was wondering if you could briefly comment on what you think is the role of astrobiology in moving forward anti-colonial and inclusive exploration.
That's probably for...
Let's go to Catherine.
That's an interesting one for which I was not prepared. I would say, I mean, any science has that kind of capacity to contribute to decolonial initiatives and to inclusion. It's a lot of it is, as you know, is just in terms of how do you practice your own science? How do you interact with those directly around you? I guess one thing I would say, and I alluded to this a little bit, is that in terms of our kind of big narratives about, because again, astrobiology does quite often invoke sort of, you know, the big story of humanity on Earth and our social evolution and things like that. I think, you know, if we can be really mindful that in the standard versions, most of humanity is left out, that say in our narratives of contact or collapse or whatever, that the histories that most people know are deeply colonial and really not very inclusive, and that we can do better. So I think that that's one way. You know, obviously, again, as an anthropologist, I would say that we could do a better job of weaving these bigger, more inclusive pictures into our ideas of you know, who humans are, where we've been, and where we're going. That's kind of the two suggestions that I have.
Awesome.
I'll stop now. Great question.
I think if anyone can have the global perspective and from deep time, it should be us. So hopefully that's what we can find. And that's one of the reasons that I care so deeply about these ascent narratives, which don't really match up with the global perspective. Lynn.
What I'd like to do is tie that in with Rosalba and Chris McKay's talk earlier, that the most extreme environments on the Earth today are the ones where it tends to be the most marginalized people, but there are canaries for the future. And so in our own work, you know, doing field work in places like the Rift Valley in Africa and so on, we've tried to bring in the local communities because they're the ones that have their finger on the pulse of the change.
Please.
Thank you for the inspiring panel. So in 1937, René Descartes said, "I think, therefore I am." And in the 1880s, Auguste Rodin, the artist from France, created a sculpture called The Thinker. You might have seen that, very, very famous worldwide. So I'm curious, with this interdisciplinary field here, instead of looking at rocks and cells and enzymes, to what extent are we challenging ourselves to examine ourselves and how we philosophically think about our feet on the ground in the environment, our soma, how we think about who we are, not only philosophically, but psychophysiology. Okay, because if we're going to inquire about what is Earth out in the universe or in other parts of the planet, how are we coming from where we are at itself? So I'm curious for the panel, but anyone else in the room who's asking questions like that, I'm curious about that.
I'm going to say, come play with us at Social and Conceptual Issues in Astrobiology, because we are all about that question. And I think Catherine and I would both love to talk with you more about that. It's a great question that has biological components that aren't differentiable from the psychological components.
Thank you.
Please.
Hi, Tessa Fisher, ASU. So Michael Wong already touched on this a bit, but it's something I've always noticed, especially as someone coming from a background in ecology, is there's an assumption in astrobiology that civilizations are growth-oriented. And I don't know if we can make that assumption because, well, even in our own human history, a lot of cultures have been growth-oriented, many have not. And in particular, the current setup of our economy, in which growth is integral, is a very recent development, only within the last few hundred years. So can we really, should we be using that as our guiding assumption, especially if we're looking about deep time? I don't want to say we should be eating the rich, but we should be eating the rich.
We tend to extrapolate from 1850 to 1950 growth patterns infinitely into the future, which is a very interesting choice, why we picked that period, but that's the period of exponential growth that tends to be projected. Please.
Yeah, hi, Jacob Huckmisser, Blue Marble Space. So I would not be doing my job if I didn't bring up technosignatures here. I'm fully sympathetic to this idea that the future of Earth is one of the understudied of the three goals of astrobiology. And I'm encouraged that NASA in particular and other agencies are taking, and private agencies are taking this search for technosignatures seriously. And that's a great intersection for the future of life and the future of life on Earth and the search for life elsewhere. A lot of SETI people have been doing this implicitly. You project from Earth today as to what kinds of things might be detectable for the future. So I think just keep thinking about this, because this is a good application to keep getting more of these future of life on Earth ideas out into the astrobiology community.
Awesome, thank you. And I would say, how do we move that from implicit beliefs about the future of civilizations to explicit beliefs about the future of civilizations? How can we use methodologies like perhaps Michael's and Kat's to move us forward into being clearer about what information is driving our predictions? I know Carlos had a question.
I mean, I have a thought on that, which actually gets to the question that I had. So you brought up SOCIA a little while ago. Last SOCIA, not this one, but the one in 2020, there was a speech by Robert Kennedy III, who was not that Robert Kennedy, but he was talking about the kinds of drives that it would take to get a spacecraft out of the solar system and the amount of energy and the fusion reactions that you would need. And apparently the limiting factor is boron, which you'll have to go to that paper for the evidence on it. But it turns out we are running out of boron on this planet within this generation. So it is entirely possible that we are making it so that we won't be able to take the vast majority of bodies out of this this solar system, but we might be able to send technology. That might be easier.
Any last words from Lynn or Rocco?
I definitely want to thank you for having this panel and for having this session, because it's something, again, I feel passionate that it should, well, it is in many ways the most important part about astrobiology, because it's us living forward. And I regret for not having mentioned the near future and the potential for using synthetic biology to help getting us off planet. But that being said, again, thank you for running this, because I think it's brought up a lot of issues that people should be aware of in this community.
Thank you.
One last comment, and that is, I just want to reiterate that I think that there have been few publications in the area of the future of life, especially the future of life on Earth and where it's going and what we may do to study it. And as the editor-in-chief of the International Journal of Astrobiology, I'm going to make a plug for the journal and also a sales pitch saying that those of you in the audience or those of you who know other people out there who are interested in this field, who would like to write an opinion piece or a review or even something that has some basic research in it and data or models, please come and talk to me, because those are the kinds of papers, I think, that spell the future for astrobiology, and I would like the journal to be part of it. So I welcome you to come and talk to me, please. Thank you.
Thank you to everyone on the panel, to the people joining us online, and thank you for coming. Hopefully we will continue these conversations for the rest of the conference and going forward.